Okay, so let's start. So today we are very happy to have Jeremy Green from Trinity College. So today we have one of our own people. So he will talk about baryon-baryon interactions and the H dibaryon from lattice QCD. So please start when you are ready. Thank you.
All right, thanks a lot. So I'm happy to, having been here just a month, I'm happy to have the opportunity to talk about what I've been working on, particularly in the last couple of years. So of course, it's in the title, and many of us here do QCD. So this is, as I think we all know, this is the elementary theory describing the strong nuclear force. And the ingredients are sp3 gauge symmetry, and gluons and quarks that are colored objects. Now, of course, gluons and quarks are not what we see in the world in terms of the actual states in the spectrum. What we see are the color singlets. And so the simplest picture has worked pretty well for decades. It's a quark model. And in the quark model, the standard participants are the QQ bar mesons and the 3-quark baryons. But in the last few years, there have been more and more experimental results for things that don't fit into the most traditional quark model. And these things, you can call them exotic. So we can go through the possibilities. So with 0 quarks, this is a glue ball. And this is quite interesting, but it's hard to disentangle this from the flavor singlet meson. So this is it's some work, and the distinction might never be totally clear as to what's a glue ball. So with 1 to 3 quarks is something we know pretty well. You can't have a bare quark. Then we have standard mesons and baryons. And in the last few years, we've had a lot of evidence for more interesting exotic particles. We've had tetraquarks, or it's kind of the debate about what these particles actually are, whether it's conceptually a compact object, like a quark model state with 4 quarks or 2 quarks and 2 antiquarks, or if this is more like a molecule or nucleus where you have 2 mesons that are loosely bound. The most recent of these from this last summer was this so-called TCC state that really unambiguously, from its flavor quantum numbers, it has 4 distinct quarks, or two charms, and a U-bar and a D-bar. And before that, we had the charged charmonium, and also there are the X and Y states that don't fit into the standard quark model predictions. So there's been a huge effort to understand these. And we've also seen petraquarks coming from LHC studies that look like perhaps a proton plus charmonium. So what I'm looking at in this study is the 6-quark sector, something you might call a hexaquark or a dibaryon. Now, of course, there is one that's extremely well known in nature, this is the deuteron. But from this sort of molecule versus compact state picture, I think you would generally call it a deuteron, so-called, you call it like a proton-neutron molecule. It's bound by just 2 MeV. And it's described quite well as a bound state of these 2 particles, not as some kind of unique compact 6-quark state. And particularly what I've been looking at is this conjectured state called the H dibaryon, that at least is originally conjectured. The idea was it was a genuine hexaquark-like state that has 2 up, 2 down, and 2 strange quarks. Now, nuclear physics is something that we would like to be able to study from first principles. And of course, the interaction between nucleons gives rise to all of nuclear physics. And one question that we could potentially answer through ab initio calculations is getting at how fine-tuned the parameters of the universe are. There's one very famous case, which is the Hoyle state. This is an excitation of carbon-12, and it's very finely tuned energy that allows carbon to be produced in large quantities in stellar nucleosynthesis. And if it was a little bit different, this would not be able to happen at such a rate. and the abundance of carbon would be much different in the universe. In the 2-nucleon sector, we can look at Big Bang nucleosynthesis. This is from the early universe, when, as the universe was cooled, you started to form nuclei. And it's a bottleneck, being that there's only one bound state of 2 nucleons. This is the deuteron. And the binding energy of deuterium, or the deuteron, is quite small, meaning the universe had to cool enough that deuteron would be stable before Big Bang nucleosynthesis could go on. And so this really controls the abundances of the light elements. And so a question that we could ask is, how strongly does the deuteron binding energy depend on the quark masses? And could there even be other bound states, like dineutron state? And so by doing calculations from first principles, you can see how fine-tuned things are, and whether, if the quark masses were a little bit different, the universe would look quite different. Now, I was just talking about nucleon interactions. If you include strange quarks, this is a situation of hyperon interactions, and these aren't nearly as well known from experiments, because of course you don't have stable hyperons to play with. And in particular, there's been a question for some time about whether strange quarks play a role in neutron stars. If you allow another species, if you allow lambda baryons to exist in a neutron star, then this can relieve the Fermi pressure, and this leads to quite different predictions of the properties, and in particular the maximum mass of neutron stars. Now, we've detected neutron stars that are the size of two solar masses or even bigger, and this really is not consistent with these earlier predictions about the effects of lambda baryons. And so this is a situation where we really need to understand these interactions much better in order to improve these models. And so it's been suggested that perhaps interactions between hyperons, which are quite difficult to measure, or 3-body interactions play a role in changing this picture. So on the subject of hyperons, as I said, the main focus, at least initially, that I'll talk about is the state conjectured almost 45 years ago, called the H-dibaryon. It's based on MIT bag model style calculation. And it really was, the idea is that this is a compact state with 2 up, 2 down, 2 strange quarks. From the SU3 picture, SU3 flavor, this would be a singlet, and it's a scalar. And the initial prediction was that its binding energy would be about 80 MeV. So there have been some attempts to find an H-dibaryon from experiment, and the most, at least the strongest constraint, the most well known, is from a single event observed at KEK, where they found a helium double hypernucleus. It's essentially an alpha particle plus 2 lambda baryons. And the energy required to remove the 2 lambdas is just under 7 MeV. And the idea is that if there were a deeply bound H-dibaryon, then there would be a strong decay where this hypernucleus would decay to an alpha particle plus H-dibaryon. But instead, the state decayed weakly, double weak decay. The 2 vertices are here and here. And this implies that if there is an H-dibaryon, its binding energy is less than about 7 MeV. More recently, at LHC, Alice has been studying baryon-baryon interactions by looking at momentum correlations in particles coming out of their fireballs. And there's some modeling required, but they were able to put some constraints on the lambda-lambda interaction. And within the available parameter space, there's still a small segment remaining that allows a bound state. And it's actually in the same range, so this goes up to 6 MeV. So it's in the same range that's allowed by that previous Nagara event. And it's been suggested that in a different scenario where the H-dibaryon is very deeply bound, where it's either a stable particle or because it only has double weak decay, it's almost stable, that it could even be dark matter. This is sort of the idea that you don't need to extend the standard model. Maybe dark matter already exists. So this idea was raised and it got some attention in the media. Now, some papers in response to this said that this idea doesn't work from the perspective of cosmology and astrophysics. But of course, this is a question that you should be able to answer within QCD. As you know, I work with QCD, and if you could, I think you should be able to actually answer the question: does the particle exist? And just because QCD is hard doesn't mean you can conjecture whatever state you like within its spectrum. Okay, so before getting into the details of the calculations, this is a preview of the main result, where most of these points, I'm showing the binding energy H dibaryon for lattice calculations with different quark masses and different pion masses. Most of these points are previous calculations, and the main result I'm showing here is this diamond with a small error bar inside. And the main result that I hope you'll be convinced of at the end is that you shouldn't trust the previous calculations. They're all affected by control systematic errors. And at this particular unphysical quark mass point is bound by 5 MeV, which is really not the steeply bound hexaquark type state. And in nature, for physical quark masses, it's probably not a bound state. Okay, so the tool that I use is lattice QCD. It's a way of formulating QCD in Euclidean space so that you can do the QCD path integral on a computer. The two important scales are little a, this is the spacing between the lattice points for your discretized spacetime, and L, which is the size, the length of the periodic box. This is the torus. And the key feature, the selling point of lattice QCD is that it is a systematically improvable approach. In fact, it's the only one we have for doing QCD calculations at low energy. And systematically improvable means that whatever approximations you make, given, for instance, finite lattice spacing and finite volume, the impact of this could be made arbitrarily small. Now, this does require increased effort, either numerical or conceptual or some combination. And so, standard thing to do is to repeat your calculations with multiple values of the lattice spacing, multiple values of the box size, and extrapolate these to 0 and infinity. And in addition, sometimes you use heavier than physical quarks, and you have to extrapolate down to physical quark masses. This is because having heavier quarks reduce the range of scales in the problem and make it numerically much more tractable. So the lattice QCD universe, it's basically taking the standard model and picking out a certain sector. So it's part of QCD, so we include gluons and some of the quarks, and it's pretty common to use only up, down, and strange quarks. And we prefer to use physical observables like the pion mass rather than something that's scheme and scale dependent like quark masses. And so we set some bare quark mass, but in the end, what really matters is the pion mass that comes out of the calculation. So we use heavier than physical pion masses, which translates to heavier than physical up and down quarks. Some of the jargon, you might see NF equals 2 plus 1. This generally means that you have an up and down quark that have equal masses and a strange quark that has a heavier and different mass. And some of the calculations I'll talk about are NF equals 3, which typically refers to having 3 quarks up, down, and strange with all equal masses. So we want to find something about the bound states in the system. And so this is spectroscopy. So the easiest thing to do is to have some operator, I'll call it O, that annihilates states with the desired quantum numbers. So if you care about a proton, you create some operator that has UUD with some spin structure and the right color structure. And then you compute a 2-point function. This is the so-called time momentum representation. So you'll have also a definite momentum. And then in Euclidean time, if you insert complete states between the source and the sink, and you work in a regime where it's a vacuum on the outside, this decomposes into a sum of contributions from all the states in the spectrum, where you have an overlap factor given by how much this operator creates a given state, from the vacuum, and a prefactor that is either the minus the energy times T, because we're in Euclidean space. And so if you go to very large separations, all the higher states decay faster than the lowest state, and you're dominated by the ground state. And so you can define something called an effective mass. This is like essentially a discrete derivative of the log of this correlator. And the effective mass will, at large time separations, approach the ground state energy that you want. And there are corrections coming from the first excited state. This is what it looks like in practice. This is some data for the proton 2-point function. It's on a semi-log scale, and you see this nice exponential behavior. Now, if I take the effective mass, you can see at late times it's plateaued. This is what we want. This is how you identify the ground state. But then at earlier times, there are excited state contributions. These are the additional exponentials that have to go away. But you also see here is that the noise grows. So this is what limits us from just going arbitrarily far. And this noise is a famous signal to noise problem. And it's really at the root of why these calculations are not simple. So if you look at the 2-point function for the proton, when you actually evaluate on the lattice, you have to, we always do the fermion path integral analytically. And so this means we have to compute quark propagators. And so you evaluate as the real part as something that involves 3 quark propagators. Now, how do you determine the noise in this quantity? Well, this is something we're evaluating in Monte Carlo. And so this is a statistical system, and it's a standard formula for the variance of some observable. So you work it out, and there are many contributions to this. But the worst contribution comes from the term where you have the quark propagator 3 times and its complex conjugate 3 times. Now the issue is that complex conjugate corresponds to an anti-quark propagator. So you get some system with three quarks and 3 anti-quarks propagating from the source to the sink. Now what happens is at late times, this will be dominated by the latest state that can contribute. And the latest state is something that looks like 3 mesons, and the latest meson is the pion. So in the end, when you form the signal to noise ratio, this is something that will decay exponentially with the nucleon mass minus 3 has the pion mass times T. And so we like to go to large times to eliminate the excited states, but unfortunately we have a noise that's growing exponentially relative to the signal. And when you go to 2 nucleons, this problem squares and it becomes much worse. And so this is why nuclear physics, well, part of the reason why nucleon-nucleon interactions are very difficult. So one thing we can do is improve the spectroscopy. And ideally, you can isolate the ground state earlier before you hit the noise problem. So a natural thing is to set up a variational system where you have rather than one interpolating operator, you have some set of n operators, and you want to find a linear combination that gives you the ground state the fastest. It turns out the way to do this is to construct a matrix of 2-point functions. This is more data to compute in your lattice calculation. But once you do this, you have this generalized eigenvalue problem. And when you solve it, you get not only a better correlator, a better effective mass for the ground state, but also you can isolate the lowest end states. So this is an approach that's been used quite widely now, and it works quite well. And just to illustrate, here I'm showing estimators for the 3 lowest states in a particular system. If you use the variational approach, you get these purple points. There's a plateau for the ground state here, first excited state here, and second excited state here. Whereas if we had taken the individual operators in this variational system, and you might even say that the second and third operators are sort of good guesses for operators that couple to the first and second excited states. However, these operators always have coupling to the ground state. And so the problem is that eventually these green points, which result from using a single operator, they will always eventually decay down to the ground state. And so what happens is you can get maybe a false plateau, but not only is it not the true plateau for this correlator, it's also not actually the correct energy level. And so particularly if you want to get excited states, it's absolutely essential to have a proper variation setup. Okay, so now if we have a method for getting the spectrum, the next question is, what does the spectrum mean? So in infinite volume in QCD, we have these isolated stable states, proton, baryon, deuteron, and so on. But above multi-particle thresholds, it's all continuous. So you have a nucleon-pion continuum with various relative momenta, nucleon-nucleon, and so on. Now in finite volume, we only have discrete levels. So the question is, what can you get out of these discrete levels that really don't look like the infinite volume spectrum? Now let's think of three cases. The first one is the easiest one. These are the isolated stable states, like a proton or a pion, and they are affected by the finite volume, but not so much. So if you think of a proton, what can happen is you can exchange a pion with its periodic neighbor, and so this will distort its energy a little bit. And so it's been shown that the energy you get in the finite volume is the mass of the proton plus some exponential correction. And the scale for this exponential correction is given by a lattice state in the spectrum. Lattice state you can exchange, which is the pion. Another case is for a stable bound state of two particles. I'm thinking here a weakly bound state like the deuteron. Here you can write it as the sum of two terms given by, if you imagine you have a scattering state of neutron and proton, and in order to get the mass of the deuteron, you need to have negative p squared, so this is imaginary momentum. And recall the magnitude of this imaginary momentum, the binding momentum. And the inverse of the binding momentum gives, in some sense, the typical scale of the size of the bound state. And it's been shown formally that the energy level in the finite box is given by the infinite volume deuteron mass plus something that scales exponentially with the binding momentum times L. Now this can be smaller than pion mass, at least finite volume effects are worse, but they are still exponential. And finally, in the case where it's an unbound state, in infinite volume, of course, the lowest state will be at threshold. And in finite volume, you also get a state at threshold, but with some displacement that goes with the power law. And these power law displacements actually give physics, you can get physics out of these, thanks to quantization conditions. Now, it's actually pretty easy to understand quantization conditions in one dimension. So let's think of one-dimensional quantum mechanics. So start with a free particle, and to make it even simpler, I'll focus on even wave functions. So for a free particle in a periodic box, so first of all, free particle means psi of x will be cosine of p times x. And in a periodic box, it has to match up at the boundary, and so you get the quantization condition p times L is some integer multiple of 2 pi. Now let's turn on some potentials. Now let's suppose that you have some potential, but it's finite range. Okay, right now the potential is actually set at 0, but I'm going to turn it on shortly. But what happens is the potential induces a phase shift of the outside region. So you still get, of course, in the outside region where there's no potential, you still have cosine waves, but they get shifted. So if you were to extrapolate these plane waves, they don't have to meet up in the middle because the potential can distort the wave function. So now, as I turn on, increase the phase shift, you see what's happening is this is getting squeezed, because if you still have to meet the finite volume, meet the periodic boundary condition, but you have a phase shift, this actually, in this case, this is increasing the energy of the state that can fit in the box. And so this shifts the finite volume quantization condition to be p times L plus the phase shift at that momentum is equal to 2 pi times the integer. And so if you didn't know what the potential was, but you did your calculations and you got the energy or the momentum of the state, you could then plug it in this formula, and this would tell you something about the phase shift. In 3 dimensions, it's more complicated, but it's the same basic idea. It's worked out first by Lucia and then extended by various people over the years. In general, it's a relationship between the infinite volume two-particle scattering amplitude and the finite volume spectrum. And it can appear in different forms. And generally, it's some kind of determinant condition where one term contains the scattering amplitude, usually if it's written in partial wave basis, and the other term is a special finite volume function that depends not only on the energy, but also on the box size and the total momentum of the frame and other parameters. And because you have reduced symmetry in a cubic box, this can also induce couplings between, for instance, S wave and D wave if you're in a moving frame, for instance. So the total angular momentum is no longer a good quantum number in the finite box. Now,
question.
Yes.
Previous one in 2 dimensions actually is a very powerful method which called bet-ansatz. That's how they do bet-ansatz in cases when they know how to write this wave function in infinite line. In 3 dimensions, again, I mean, I understand Lucia did it and so on. This seems to be not that powerful.
It's been used quite a lot for lattice QCD calculations in it.
Was it? Yeah.
Oh yeah, tremendously.
But only lattice. I mean, the previous one, again, if you go back, that's how bet-ansatz was basically invented in a sense, at least reinvented maybe. And it's maybe the difference is that the procedure, of course, is general on previous page, but if the theory is integrable, then it's powerful. Here, in 3 dimensions, it's never integrable, probably. That's why it's not powerful. Is that true?
I really don't know. So here, I use this in the very simplest form, where I ignore all the higher partial waves. And in this case, this k tilde inverse becomes p times the cotangent of the S wave phase shift. And this combination is a useful combination because it's real and analytic across the threshold, even below threshold is real and smooth. And on the right-hand side, you have some funny generalized zeta function that has poles at all the non-directing levels. So with this equation, you can use it in 2 ways. So in one way, if you do your calculation and you get the energy of a state, you translate it into a back-to-back momentum p of the scattering particles. And you can plug it into the right-hand side, and then you get the phase shift at that particular point. So you do a calculation, you get one level, this gives you 1 point on the phase shift curve. You can also use it the other way, where you have some ansatz for the left-hand side, and then you find all the solutions to this equation, and this gives you the spectrum predicted from that ansatz. And that's actually a common way for actually fitting to the lattice data. You have some ansatz, plug it into the quantization condition, turn the crank, find the spectrum, and then compare this with the lattice spectrum when you're fitting. And a key point here is that there can be residual finite volume effects, but they're again given by the lattice state, the pi mass times L. So as long as m pi times L is 4 and a reasonable size, then these are suppressed. And in fact, I use it below threshold. So you write scattering amplitude in terms of the phase shift. It has a pole whenever this denominator here is 0. And so by solving for poles below threshold, this is the way we actually identify bound states. Rather than just going directly from the ground state in the lattice, I use this indirect method. And in particular, this is useful because it avoids these potentially larger finite volume effects that scale with the binding momentum. Okay, so now getting to the H-dibaryon. It's something that people have studied for quite a long time in the lattice. The first calculation was as old as I am, and by today's standards, of course, it's laughable in 6 squared by 12 by 18 lattice. This is obviously this isn't This is not what we do nowadays. If I trim down the calculations that have been done by including only those with dynamical quarks, that means the quenched approximation is not acceptable. Then, other than the work I'm talking about, this has only been done by two collaborations. One is NPL-QCD, and they use the methods based on spectroscopy, and then the other is HAL-QCD that have their own methods based on baryon-baryon potentials. And in both cases, they found bound states for heavy pion masses, and sometimes quite bound up to 80 MeV. So the project that I'm talking about, this is with the collaboration that's generally referred to as the Mainz collaboration, because people joined it when they were at Mainz. I joined it several years ago when I was a postdoc at Mainz, and people then spread out. So we have one paper that's published a couple of years ago, and then more recently, the second work is the main one I will talk about. And I should highlight Drew Hanlon, who did a lot of work also on this particular paper. So the first question we addressed, and this is for the first paper, was interpolating operators. What operators should you use actually to produce these states? And the most natural, there's really two natural kinds. One is the hexaquark operator, where you have 6 quarks at the same point, and this looks something like the quark model state. And the other is what I'll call a 2-baryon operator, where it looks like one baryon with momentum P1 and the other baryon with momentum P minus P1. And so here you can actually get many operators because you're varying the relative momentum of the 2 baryons. And so this one looks something like a non-reacting state, 2 baryons. And it gets even more complicated, because once you decide the operators you want, then the question becomes, how do you actually compute these correlation functions? And a very common approach, it's very popular, is to use point sources. And with point sources, you can, of course, go from your point source to a point sink with all those 6 quarks at the same point. This gives the hexaquark type interpolator, or you can have hexaquark interpolator at the source and a baryon-baryon at the sink. But you can't easily do baryon-baryon at the source and baryon-baryon at the sink, because the baryon-baryon source is not local. It's bilocal. So in fact, many calculations have been done with only this type of correlation matrix. It's an off-diagonal correlation matrix. And a big downside of these is that the correlators are not positive definite. And so in particular, the effective energy is not an upper bound on the energy. You can approach from below, and you can be misled because of that. And so in this first study, we compared these two types of correlation functions you can get from point sources. So here I'm showing the effective energy in the H-baryon sector, where these green points are from the hexaquark only. It's the diagonal correlation function. So the effective energy has to approach from above. And you see, of course, it comes down and it plateaus with quite a bit of noise. This black horizontal line is the threshold, so you can't really tell whether the state is above or below threshold because it's too noisy. The other ones all involve, to some extent, these baryon-baryon operators at the sink. Now what you see immediately is that the noise is much better. So somehow these baryon-baryon operators are giving a much better statistical signal. But what also happens is you can get, most strongly for these red points, you can dip down and then come back up. And the danger here is that at the same time you're losing your signal. So what could happen is it dips down and then the error blows up and you think, there's my plateau down here. So this is a tricky thing. This potentially leads to some underestimates of systematic uncertainty. But from this, we really decided that, okay, these baryon-baryon operators are important. And so we invested the effort to develop a new methodology that allows us to use these at the source as well and have these positive definite correlation matrix. And so we use, I'm just going to ignore that. So we use this method called distillation that was developed in part by Mike Bearden here at Trinity, and involves using as your sources, I'm not expecting anybody. Using as your sources, all right, I have to check that, I'm sorry. I'll try to be as quick as I can.
Okay, go ahead.
Sorry, I have broken doorbell. So distillation, the idea is to use something that's non-local, using low modes of a gauge covariant Laplacian as the source for your quark propagators. And so this gives you a kind of time slice to all quark propagators. And so this allows us to do these baryon-baryon to baryon-baryon correlation matrix. Now, the tricky thing is that we have to scale the number of modes with spatial volume, and the cost of these, simply the tensor contractions, scales with n to the fourth. And so as you go to bigger volumes, this will rapidly become a problem, but at least for the calculations we've done, the cost of these contractions has been manageable. So here, this is our comparison, where what I'm showing instead of the effective energy is actually the effective energy difference between the effective energy for the ground state of the H-dibaryon system minus twice the effective energy of a single baryon. Now here, distillation, it's almost too good. It's very flat. It's flat immediately. There's a lot of cancellation happening between these two terms. So, but it's also much more precise. And so from this, we concluded that we really have to use the distillation method. It's so much better than point-to-all methods. And in fact, the computational cost of these two is about the same. So this is the way to go forward. So this is the main results of this first paper, was just establishing methodology for spectroscopy. And so from that, we can use the Lucia method. So we got this red point was the ground state in the rest frame, and then by changing the total momentum, you can probe different kinematics. So here I'm showing p cotangent delta versus p squared, and so only this very tiny blue point comes from distillation. The rest are from the other method, the point source method. So then when we fit to these points, we look for the intersection with this orange curve, and this gives us the bound state pole. So that binding energy was 19 plus or minus 10 MeV from this calculation. So having established a good methodology, now we wanted to really tackle other systematics. So that was all done in a single ensemble. This is what I showed was a single ensemble. But now we really want to study these other systematics. And so we used 8 different ensembles, where here, this is different values of lattice spacing on the x-axis and different box sizes on the y-axis. Now, the one caveat is that we didn't vary 2 parameters. We kept a third parameter fixed, and that's the quark masses. So this is an SU3 symmetric point. This means up, down, and strange quark masses are all equal. And in fact, they are set to the average physical value of these quark masses. It means the pion mass is 420 MeV. And so we use distillation and these baryon-baryon interpolators everywhere. And this really allowed us to do a careful study of systematic effects. Now, this is at the SU3 symmetric point. And so you can talk about protons and neutrons and other lambdas and psi baryons, but they all belong to an SU3 octet. And in this case, it's an exact symmetry. So I prefer just to say octet baryons. And then if you, in the flavor structure, if you combine 2 octet baryons, it's a symmetric combination, which belongs to 3 different SU3 EREPs, and likewise for the anti-symmetric combination. So we looked at just the singlet, which is the sector in which the H-dibaryon is supposed to live. Oh dear, hold on. Sorry. So now we want to get the spectrum. And so in most frames, we use a 3x3 correlator matrix. So it's still not a huge number of interpolating operators, but it's reasonable. And again, we focus on these effective energy differences. So we perform the diagonalization and take the ratio of the diagonal correlator to two single baryon correlation matrices that correspond to a nearby non-interacting level. And so here is some typical example where these are 4 different lattice ensembles that have roughly the same volume, but different lattice spacings, and showing the effective energy difference for one particular state. And the orange points are the coarsest lattice spacing, and as you go to darker points, more purple points, you get to the finer lattice spacings. So here, this was the big surprise, which was as we vary lattice spacing, it's not a small effect, but this is, these levels are moving by tens of MeV. And so the lattice spacing effect turned out to be quite big, and which had been neglected beforehand. So here's the summary of all the data. So what I'm showing is the p squared, which corresponds to the energy of a particular energy level, versus L, and we have the rest frame here, and 4 additional moving frames. And here, these red dashed curves are what we would get if there are no interaction. So all the points are displaced from the red dashed curves because it's the fact that there is some interaction. And these blue curves are based on fits. This is what I expect for 0 lattice spacing the data should be. And finally, these points, of course, are the lattice data. And you see it's a consistent pattern everywhere, whereas you go from coarser lattice spacings, green and orange points, to finer lattice spacings, purple and blue. It's really quite a big shift in the energy levels. And so we found that these discretization effects really are quite significant. So now the question is, how do you analyze these data? So what I just showed you is essentially the energy for the given box size and lattice spacing. And what we want to get is the phase shift in the continuum as a function of the p squared energy. So the most conceptually straightforward approach, at least based on what's been worked out, is you can, if you had energy levels of the same box size but multiple lattice spacings, you could extrapolate the energy down to a continuum, finite volume energy. And then we have quantization conditions that are all worked out in the continuum. The other approach is less straightforward. The idea is you would get first some kind of scattering amplitude at finite lattice spacing. Now, finite lattice spacing breaks all sorts of symmetries, including rotational symmetry. So this might not look like a continuum scattering amplitude, and then extrapolate that. Now, one ingredient we don't have is quantization conditions at finite lattice spacing. So this is something that, at least rigorously, you can't do very well, but still, it turns out that with some assumptions and approximations, this is the approach that works best. So essentially, we assume you can use continuum quantization conditions on these energy levels of finite lattice spacing. And we found that this was able to fit the data pretty well, even neglecting possible rotational symmetry breaking effects. So essentially, we assume that this really is just one function, delta of p squared and a, and it's not. It doesn't also depend on hypercubic invariance. Okay, so again, this is the quantization condition we use, truncated to S wave. And then we have a fit ansatz. It's the simplest, one of the simpler ones we can do. We assume p cotangent delta is given by a polynomial in p squared, whereas coefficients are affine functions of a squared. And so here I'm showing, again, the same quantity b cotangent delta versus p squared that I showed for the previous calculation. And again, for these 4 ensembles, we'll have about the same box size. And you see this really moves up quite a bit. And in the inset, it's the intersections with this red dash curve that give the bound state. And you can see that these intersections are moving quite a bit as you go from coarse to fine lattice spacing, and the blue is in the continuum. And in fact, because these ensembles have similar volumes, we're able to do a small correction to adjust these to a common volume and do a cross-check following this red path of doing extrapolations at fixed volume. This is a noisier result because it assumes less about the structure, but nothing here contradicted our results. So everything seems consistent with extrapolating at fixed volume. So this is the main result showing the binding energy versus lattice spacing a squared. In the continuum, it's about 4.5 MeV, but you can see the huge change you get at non-zero lattice spacing. The coarsest one is about 30 MeV. And so all previous calculations of baryon-baryon scattering have been done at single lattice spacing with an assumption, or at least the hope, that these effects are small. Unfortunately, it seems that they could be, at least in one case, they could be quite significant. So again, coming back to this comparison in more detail, all these green points are ones that were done with SU3 symmetric setups where the strange and light quark masses are equal and reaching up to 75 MeV in binding energy. This orange band is the range we get in our calculation of finite lattice spacing, and the extrapolated result is down here. And so unfortunately, these older results seem to be all affected by a large uncontrolled systematic uncertainty. Furthermore, some of these, like these circles, were also use point source methods that I believe don't give a reliable spectrum. So maybe there are two ways you shouldn't trust them. Okay, so this was at one unphysical quark mass point, the SU3 point. If you break SU3 symmetry, it becomes a much more complicated analysis because the H dibaryon coupled with 3 different baryon-baryon channels. And so here at the SU3 symmetric point, I've drawn the 2-octet baryon threshold, and I've displaced below that. This is the binding energy we see. This is about 5 MeV. But if you go to the physical point, this threshold splits into 3 thresholds, and the splitting completely overwhelms the size of the binding energy. And so from a very naive analysis of this, you would say you don't know whether there's a bound state in the continuum. Now we have data that have been generated away from the SU3 point. Colleague Padmanabh gave a talk about this at the Lattice conference, but that's still ongoing. Now in the past, other people have used effective field theories to extrapolate lattice data to the continuum, and even those based on rather heavy binding energies at the SU3 point, they found that there's probably not a bound state in the continuum at the physical binding mass. And so now that we have a much smaller binding energy, I think it's rather unlikely there will be a bound state in the physical binding mass. Now, of course, the other sector that has a lot of attention is the nucleon-nucleon sector. Here, the situation from the lattice is really not that great. So on the left is showing the deuteron. Of course, it's bound by 2 MeV at the physical point. And there's a group of calculations that say that as you go to heavier pion masses, it becomes more bound. Likewise, there's a dineutron state that's not bound in physical. It's dashed line simply means unbound. And some groups say that it becomes a bound state as you go to heavier pion masses. But other groups have also done these calculations in these similar quark masses, and they say there's no bound state. So there's quite a big disagreement, and there was quite actually an active controversy in the literature over these. Now, one big problem that comes up is that no calculations were formed with more than one lattice spacing. And so potentially this is a large systematic uncertainty affecting all of these. And likewise, every calculation that obtains a bound state uses this sort of asymmetric correlation function that is potentially affected by the false plateau problem. So this is an area that there's a lot of room for new work, and of course I have data on this, and it's in the pipeline. So in summary, I would say it's absolutely essential to use a variational method to determine the spectrum, and it turns out the discretization effects can be very large, and so it's also essential to have multiple lattice spacings. And the implication is for both of these is that unfortunately most previous calculations in multivariate systems are affected by uncontrolled systematic errors. Now, the positive aspect is that this standard lattice methodology has been used quite a bit in the meson-meson sector, can work quite well for baryon-baryon interactions, as I've shown. And so I'm optimistic that we will get reliable results for nucleon-nucleon moving forward. The H-dibaryon turns out is weakly bound at the SU3 point and probably not bound at the physical point. And the fact that we need fine lattice spacings in addition to controlling the noise problem means that calculations of physical biomass are going to be challenging. Thanks.
Okay, so let's thank Jeremy for the very nice talk. And then we can open for questions. So if you have a question, please, you can unmute yourself.
Yeah, hi, Jeremy. Very nice talk, thanks. So I just have a quick question. So in your variational basis, you have to throw out the dibaryon operator, right, when you're using distillation? Just because
yeah, the hexaquark, yeah, the contraction cost would be much higher. So
right. So
throw it out.
are you then concerned that that affects your ability to pin down the energy at close to threshold or not?
It would be better to include it. There was actually a study that came out quite recently by NPL-QCD where they were looking at nucleon-nucleon, and they found that whether you include hexaquark or not, it doesn't affect the low-lying state. So they did find an extra state that was higher in the spectrum that we don't understand yet, but at least the lowest few states weren't affected. Actually, all the states weren't affected except for the extra one. Now here we can do consistency checks. We can look, the quantization condition predicts where all the levels are, and the fact that we can describe our levels with a single curve. This is an indication that the data is self-consistent, and so it would be difficult to shift everything in a funny way. So I'm not overly worried about the hexaquark operators.
Jeremy, can I ask, in your summary plot for the H-dibaryon, where you have your very nice precise result, you could argue that the NPL, I think it's the NPL QCD result is consistent. I mean, they have very large uncertainties,
Yeah.
especially at that lighter pion mass. What's the prospect for them shrinking the uncertainties? What's the dominant uncertainty, maybe, is the question.
I don't recall precisely, especially these lower ones. I mean, obviously the latest one is statistical, it's quite big. Yeah, so I don't know what their uncertainty came from. I believe they actually are moving toward the variational setup as in the recent publication, although they've not published on the H-dibaryon in a few years though.
Okay.
More questions?
And if you do reduce the pion mass in these nucleon calculations, right, there must be, I mean, are you opening additional thresholds, scattering thresholds, and that you have to worry about?
Nucleon, okay, the 3-particle threshold comes down, of course.
Yeah.
But I would say the noise problem is the biggest issue. The fact that you have a more narrow window is not such a big problem.
Okay.
It's the H-dibaryon that gets much more complicated.
I see. Okay.
Hi, Jeremy. Thanks for the nice talk. I have a question regarding your plot where you showed the impact of distillation on the mass difference. Can you go to this plot again, please?
Yeah.
just to get a feeling, I mean, if you don't look at the subtracted mass or just at a plain mass, how does the effective mass compare in those two cases between distillation and 0.2
Yes.
I mean, from the signal to noise ratio point of view.
Yeah, I mean, unfortunately, we didn't have a plot showing precisely that comparison. So distillation gives it much smaller errors, and I think in terms of where the plateau is reached is somewhere 0.8 Fermi. It's similar to these wide open points, but it's more precise, and I think it's a little bit flatter.
Okay, so you always gain essentially from using distillation, indeed.
Yeah, I mean it's more the fact that distillation lets us use these symmetric correlators with the baryon-baryon operators rather than distillation in itself. So
okay.
for a single baryon, distillation is not really any better than point sources.
Okay, great, thanks.
But you mentioned, I think, that the computational cost was about the same in that previous plot?
Yes.
Yeah.
So there is a better cancellation with distillation. When you take 2 baryons minus twice 1 baryon, this cancels somewhat better with the distillation approach. And so you get, this contributes to this unreasonable difference in the errors here.
I see, okay.
Any more questions? Can you say something about the when you break SU3 symmetry, or like you mentioned that it was presented in a conference, so you made some progress on these?
Yeah.
If you can, if you can say a few words, I don't know.
Yeah. So these lattice ensembles were generated keeping this sum of the 3 quark masses up, down, and strange fixed. So the SU3 point here corresponds to heavier than physical up and down quark masses, but lighter than physical strange quark mass. So as you go away from that, you're making the strange quark heavier and the up and down quarks lighter. So we have data at, I think, 3 points, so 3 steps toward lighter, the lightest being at biomass 200 MeV. And so it's, so we have the spectrum that's being analyzed, and just fitting is, you can maybe light enough biomass, you can ignore this highest threshold and only deal with the 2 coupled channels, but still your scattering amplitude, rather than being 1 function of p squared, you have 2 phase shifts and a mixing angle, and it's just much more complicated to model. Furthermore, because these are unequal particles and they can cascade, this complicates things in the moving frames. You have, instead of D wave being the first neglected partial wave, higher partial wave, it becomes P wave, and it's various added complications come because of that.
Okay. Any other question? So if not, let's think again, Jeremy. It was a very nice talk. And yeah, I think that's it. Many thanks, Jeremy, for the talk.
Thank you.
Great, thanks, Jeremy.
Thanks.